Hi everyone, how are you doing? I'm good, thank you. It is
Good. How about
Monday.
you?
I'm okay, hanging in there. Hi Sarah. Hi everyone. Got a few minutes before we start. Let's download our notes and look at your assignment. Can you believe it? We're halfway done. Soon it'll be summer. Okay, so let me get my files open. So today we're going to go over sequence and series. So you can go ahead and check out Canvas, download the assignment. And then we'll go over it in a few minutes. I'm still working on your grade, so hopefully tomorrow we'll get everything updated along with my CIS7 class. So next week is spring break, right? We get a little bit of a break. So no class in session during spring break. If you're all caught up with all your assignments, then you can take a break, enjoy some time. It's beautiful outside. Okay, so it's 6 o'clock. We are gonna work on Unit 8 this week. Let me get into screen share here. Okay, so we are gonna go over sequence and series. That will be chapter 11. Before spring break, we wanna work on our homework assignment. Excuse me. We're gonna have quiz 2 when we come back. So if you finish everything by the end of the week, you don't have to worry about submitting stuff when you come back. And then we will do a quiz review game when we come back. And then we will work on Unit 9, which we will go over induction and recurrence. So this week is pretty straightforward. We're going to work on sequence, sums, and series. You can find the notes right here. It's the second page of the module. And then I added some additional tutorial videos if you want to watch those. And also the in-class assignment, we're going to go over that now. Okay. So in the notes, it starts with talking about sequence. And if you have taken the other programming classes or math classes, you will work with different sequence like Fibonacci, Lucas, golden ratio, stuff like that. So we're going to start looking for pattern or a way to enumerate a collection of objects which have some kind of repetition. And before we go into recursion, because in the next week we will implement recursive function as we solve some of the problems, okay, in programming and in math, then we need to cover the basic concept in sequence. So in sequence, you would have, in programming, we would have a container, let's say an array, and you would have the elements initialized in that array, right? And in some sequence, it will be infinite as it could continue forever. But in a finite sequence, we would have a length of the sequence would be your cardinality, or the number of the elements that you would have in that array. And so unlike the set, you can have the elements appearing the same. Like for example, I might have a 1 and a 1. Like in Fibonacci, if we seed it at 1 and 1, and we add the 2 value, that would give us the third value, which is 2, and so on. So in some sequence, you would see that there might be the same value in the elements multiple times, but in different position, right? It could be the first and the second, or it could be later down in the sequence container. So formally, we would see it as a function of whose domain either is a set or a natural number. So in some case, when we look at Fibonacci sequence, which we will do later, you would see that it can go on infinitely. And when you implement different algorithm, you would find that, how you solve your problem could be efficient or not, okay? So in a sequence, we would use the function of which the domain is a consecutive set of integers, and that could be a sequence. So when you look at the domain function, the example here, it shows you that it could denote student GPA, right, in the 4 years that they attend college. And we can look at 1, 2, and 3, and 4, which represent the year. Now, the sequence would be represented with the function from a subset of integers, or in the infinite case, that will be natural numbers. So let's take a look at the first example. So when we have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and it can continue on. So when you look at the sequence, first you have to see what is the pattern, right? We see that the denominator is increasing as the nth value is increasing. So we would say if n is equal to 1, then we have 1 over 1 for the first term. Then we can try for the second term. When n is equal to 2, we would have 1 over 2 for the second term. When n is equal to 3, we have 1 over 3 for the third term, and so on. So we can say that when it reached the 7th term, you would have 1 over 7 as n is equal to 7. So we can say that t of n, or f of n, is 1 over n. So if we need to determine the 100th term, we would say that it's 1 over 100. Okay. So we would see that there's an increment in the denominator, right, as it would represent the n. For example 11.1. In example 11.2, we have even numbers, or even integers. We would have 2, 4, 6, 8, 10, 12, and so on. So we would start with, if n is equal to 1, we would have 2 times 1, which gives us 2, the first number. Then we can say for the second term, when n is equal to 2, we would have n, right, times 2, which gives us 4. 2 times 2 is 4. And then when n is 3, we would take 2 times 3, that gives us 6. So if we need to solve for n is equal to 22, we can say that 2 times 22, which gives us 44. So if we need to find the 7th term, for in the sequence, we would have 2 times 7, which gives us 14, and so on. Okay, so these are some of the example, and what you would do when you approach this example is first, you need to determine how the nth value would play in that pattern of the sequence given each term, and we would start with the first term, right, and look at the relationship of the function to that particular term and the subsequent term. Now, another example we can look at, which is a little bit different than the last one, we have 2, 4, 8, 16, 32, 64. And so when we say that if n is equal to 1, we would have 2 to the power of n, which is 2. 2 to the first is 2. When n is equal to 2, we would have 2 to the second power. So in this example, what we see is we would have the nth value is the exponent, right? And we have a base 2. And so we can test it for each of the term, and we would be able to determine that when you have the seventh term, that would be 2 to the n or 2 to the 7th, that would be 128. Okay. And then the following example, you have 7, 8, 9, 10, 11, 12. So we do see an increment of 1 as we proceed further down the sequence. If you start with the first value, which is a, or n is equal to 1, we would have n is equal to 1. We would take 1 plus 6 gives us 7. So the n, right, we're going to add a 6. So what you need to, in this case, what we have come up with is we have to see what is the pattern? What are we adding with? What is the common value that we're adding with, right, throughout, where when we have the n is 1, 2, 3, 4, 5, we're going down the value with the n. When n is equal to 2, we would take 2 plus 6 gives us 8. When n is equal to 3, 3 plus 6 gives us 9, and so on. So we can say that T of n is n plus 6, which gives us 7 plus 6 for the seventh term, which is 13. Okay. Do one more and then we'll answer the assignment question. So in example 11.5, we start with 1/2, 1/2 for the first term, and then we go to 1 for the second term. So we would start with saying when n is equal to 1, we would have 2 to the power of 1 minus 2, which is 2 to the negative 1, which gives us 1/2. And then when n is equal to 2, we would have 2 to the power of 2 minus 2, which is 0. So 2 to the 0 gives us 1. If n is equal to 3, we would take 2, raise it to the 3 minus 2, which is 2 to the first, which gives us 2. So we can conclude that T of n is equal to 2, raise it to the n minus 2, because you can see the pattern happening, right? The relationship of that to the nth value. So if we need to determine the seventh term or the eighth term, you can simply plug in the n value. So let's say if we need to solve for the seventh term, we would have 2 raise it to the 7 minus 2 power, right? And that will be 2 to the 5th. Any questions so far? So in this one, what we would do is we would start looking for a pattern, okay? And then down the line, we would apply the formula so that way it's easier. So I want you to be able to see the sequence pattern with the numerical value first. And we can start with plugging in the n value. And when you work with proof, you're going to see some similar technique there, right? When we're trying to illustrate how the function would be able to be represented with different math law. So in the first question of your assignment, it asks you to look at S. So you have a sequence called S, and you would start with the first value as 1. And after 1 to the 10, 1 over 10, we need to determine what is the following value. So we have to first find f of n or t of n to be able to solve for the next value in the sequence after the fourth term. Okay? So we would be able to write out the equation to represent that sequence. So we would start with the first term. When n is equal to 1, we can see that f of n is 1 over 1. Then on the next term, when n is equal to 2, we would have f of n is equal to 1 over 2. Now, this one is unique in that it has the initial 2 values, okay? And then later on in the sequence, it's going to have a pattern. And you do see that in some cases. Some cases that you would have some values, doesn't necessarily be seeding values, but they are values. But the pattern picks up after, the third term or the fifth term, etc. Because data is data in some cases, and we might not see a constructive function until we look at it further down the line. So this one is a little bit unique compared to the other ones that we looked at in the example. So now when we start plugging in n is equal to 3, we would have f of n is equal to 1 divided by 2 times n, okay, which is 1 over 6, 1 over 6, okay? And then when we have n is equal to 4, we would have f of n is equal to 1 over 2 times 4. That would give us 1/8. When n is equal to 5, we have f of n is equal to 1 over 2 times 5, or 1/10. So in this sequence, the first 2 terms, there is a pattern with these two, okay? And it's a separate pattern. So the first 2 terms, your f of n is 1 over n. Okay? Then the sequence pattern starts at the third term for the rest of the sequence. So we can say that for the rest of the sequence, at the third term and forward, that will be f of n is equal to 1 over 2 times n. So the way that we write this is like this, okay? You can insert the math equation if you want to write it like this. You can handwrite it, okay? But I wanted to show you how that would be written in a math format, okay? So when you have n is 1 and n is 2, your f of n is 1 over n. But when you go to the third term and the rest of the sequence, when we have n is greater and equal to 3, your f of n is equal to 1 divided by 2 times n. Okay? And for us, when we're trying to solve for the sixth term, okay? 2, 4, 6. So for the sixth term, we would use this equation, okay? 1 divided by, so we would have f of n is equal to 1 divided by 2 times n. So that means that we can determine the sixth term by taking 1 divided by 2 times 6, which gives us 112. Okay? So we can say that our sixth term would be 112. Okay? And you can visually see that it's the denominator here is increasing, right? And so we have to put it into the equation. And so in order to solve this, we would then need to determine the function based on the pattern that's represented without using a formula. So later on, we would see that we can apply this into a formula. Okay, so any question with number 1? So when you interpret this into C++, right, into the programming, then you would write the if conditions to fulfill this part first, okay? And you would say if, right, n is equal to 1, then this would be the result. If n is equal to 2, then it will be 1 over n. Then after that, you would then implement a loop, right, starting with the third element to loop it until the end of that container. So that way we can fill in the values for all the subsequent, right, elements starting with the third term until the end, or it could go infinitely, right? Now, you know, if you wanted to structure it where it would be a function and you just call that function in the main, that's fine. So when you look at an equation like this, or you look at a pattern type of sequence like this, you should be able to see it in your mind how you would approach that in programming, right? What kind of algorithm you would implement, what kind of steps you would go through to be able to write that, the code, the program that would represent this sequence, okay? So in programming challenges, sometimes that they would give you something like this, and they would ask you to write a program to, you know, solve the problem or to display what is the value, what is f of n when it's at the 200th term, okay? So mathematically, if you solve it, right, you just have to come up with the function and then to be able to implement that with the code. Any question? Okay, so this one's a little tricky to start, right? Let's do the next one. Okay, let's do this one. Number 2. So we're given a sequence S and it has a value 5, 10, 15, and 20. So right off the bat, we know that it's multiple of 5s, right? Looking at the values that are given to us, okay? The element's value. Then it asks us what is the value for what is the next term value in S, and we want to write the equation to represent that. So we know that it's multiple of 5 by looking at the element value in this particular sequence. And we can even say that first we would start with, if n is equal to 1, we would take 5 times 1, so our f of n is 5. If n is 2, we would have f of n equal 5 times 2, which is 10. If n is 3, f of n is 5 times 3, which is 15. So we can say that yes, the common ratio in this is 5, right? Because they're all multiple of 5. So for the fifth term, that will be 5 times 5, which is 25. Because our t of n or f of n is 5 times n. Okay?
So I had a question.
Mhm.
If we wanted to, we can do the extra step just to be sure that it's correct.
Yes.
Okay.
Yeah. So you can go further. You can go to 4 or 5, right? And then to check. What I normally do is I would do a few first to really see the pattern. And then based on that, right, I would first, in this case, we would come up with a common ratio. What are we multiplying that's the same throughout each and every single step for each of the elements? We can say that the common ratio is 5 because we're multiplying it by 5, right? So the takeaway from this is you got to take a look at the relationship from one value to also the next value. Okay, from 5 to 10, from 10 to 15, from 15 to 20, right? The distance between these elements are 5s, right? So if you take 10, subtract 5, you get a 5. You take 15, subtract 10, you get a 5, right? So that validate that will be your ratio. And we'll come back to this concept when we start using the formula on how to come up with your sequence. Okay, any question with 2? Later on, we are going to we're going to look back to this concept and we're going to look at relations, right? How we're looking at values and the relationship between those values. And so this is going to expand a little further down the line, just to let you know. Good. All right. So we're good. Okay. So if you look at some of the additional example, like what we've been doing, okay? So when we left off, right? So in some cases, it might not just be multiplying with a certain value to n or dividing by n, right? You might have to take a look at how you can represent the term, the position of that number, right, of that element in that sequence, right, in addition to the differences from one value to the next. So in the example 16.6 or 11.6, you have 1, 3, 6, 10, 15, and 21. So when we have n is equal to 1, you would have 1 squared plus 1 divided by 2, which gives you 2 divided by 2, which is 1. Okay, why can't I just do 1 divided by 1? Well, I still have to consider the relationship of the next value in that sequence. So if I just simply take 1 divided by n, on the next one, it would not be correct because I need to represent 3 there, okay? So for when we plug in n is equal to 2, we would have 2 squared, which is 4, plus 2, then divided by 2. So when we square and add it, that gives us 6. And when we divide it by 2, that gives us 3. And we started to see a pattern happening because when we square the n and plus it with the n, then divide it by 2, we would get that sequence. If n is equal to 3, again, we would take 3 squared plus 3, and then divide it by 2, which gives you 12 over 2, or 6. So we can conclude based on looking at these that your T of n is equal to n squared plus n divided by 2. So to solve for the 7th term or the 20th term, you simply plug in the position value or the n and be able to come up with your output. Okay. So this one's a little bit more complex. Then we can take a look at the next one. So what if you have a sequence of ones, right? There's a pattern there. They're all ones. 1, 1, 1, 1. So if you start with n is equal to 1, we would take 1 divided by 1, which gives us 1. If n is equal to 2, we would have 2 divided by 2 gives us 1. N is equal to 3, 3 divided by 3 gives us 1, and so on. So we would conclude that our function is n, T of n is n divided by n, or 1. Okay? So a sequence, again, unlike the set, you can have the repetition of that value. It's just in a different position. Okay. So the earlier number 1 example, it would look something like this, right? And then more of a complex example, you would see something like 11, 9. So Jesus says, so in the last example, you mean n is equal to 0. Good point. Okay. So Jesus may recommend that what if we use n is equal to 0, right? So for the first one, that would be 1 to the 0. The second one, 2 to the 0. Yeah, that would still be the same. You can also have, so that can also be your T of n, right? Can also be n to the 0. That's good that you saw that. How many years I teach this class and nobody actually brought that up? Good point. That will work as well. Okay. So now let's take a look at the next question that we have to solve. Okay. So for number 3, it gives you a sequence of 5, 7, 4, 14, 321, 228, and etc. Okay. What is the next term in the sequence? Write the T of n equation that represents, that represents the above sequence. I'm just looking at my dog and hope he doesn't fall down. I'm sorry. I have a dog that has a very large tumor and he falls down sometimes. Okay. All right. So first we would then plug in our n, okay, before we would solve for the next one. So when we start with n is equal to 1, we can see that we would have 6 minus 1 divided by 7 times 1, because we have to represent the 1 in the 7 and the 1 in the 5, right? So to get a 5, you would take 6, subtract 1, or the n is equal to 1, and then you would take 7 times 1, which gives us 7, so we have 5, 7. If n is equal to 2, we would take 6 minus 2 divided by 7 times 2, which gives us 414. And we don't have to reduce it. We want to leave it like that so we can see a pattern that's repeating, okay? And then if you want, you can go further and solve for if n is equal to 3, and so on. So when we can conclude that your t of n is 6 minus n divided by 7 times n. So if we need to take a look at the 5th term in that sequence, we would plug in the 5, right? So this one is for the 5th term. We would take 6 minus 5 divided by 7 times 5, which gives us 1 over 35. Okay, and yes, you can, earlier Sarah asked if you can do a couple more steps to really verify it. Sure. Because sometimes like the first one, right, after the first two, it might change. So we wanted to continue, but I wanted to only write out a few steps here so you can see. Okay, so if you want, you can do if n is equal to 3, write t of n is equal to 6 minus 3 divided by 7 times 3, which is, then you would have 3 over 21. That's what we see here. Okay. And so on. Any question? Okay, no, we're good. So Rashad asked, can there be multiple ways to solve one sequence? Sure, right? Ultimately, what are we looking at? We're looking at how your sequence is represented in the relationship of n, or the position of that element. Because in the programming side, the position means what? Index, right? When you're accessing the index is where you are accessing the value of that element in the container. So how will you be able to take the index value and represent that as the element value in that sequence? Okay. And in some cases, that's true that you might have multiple equations to represent that, right? Earlier, we saw that we can use n to the 0 or like an exponent to represent that, or we can use division to represent that. And we can draw the relationship between those two functions, but, you know, and then there's some sequence that there will be one way to represent that, and that's the only way, right? So you do see some cases that you do have multiple options in writing out the functions, okay? And mathematically, there are ways to, you know, derive your solutions, you know, using different steps, of course, okay? Okay. So here we solved for 3. We came up with our equation for t of n, and then we would find the fifth term. Okay, so before we go into 4, I want to proceed a little further so you can understand what we're doing on the notes. Okay, so you can practice looking at these. Okay, so we warm up with these, and then we would differentiate the type of sequence. Okay, so in the next part on page 3 of your notes, it talks about arithmetic sequence. And arithmetic sequence is a sequence that each term equals the preceding term plus a constant. Like when you're adding a 6 to every value, okay? So we're looking at, right, the distance across, okay, from one value to the next value down that sequence. So it says that in the arithmetic sequence, the difference between the consecutive terms is always the same. And that's the key area, is that when you're looking at an arithmetic sequence, from one term to the next term, the difference of that is the same constant, the constant. So, and sometimes you would hear it referred to as arithmetic progression. Okay. So when we look at how it's written, we would then start with the first term, which is a. Then we would add a to that constant, which is d. And then on the third term, that will be a plus 2d, and then a plus 3d, and then a plus 4d, and so on. So based on this, we also see how we can represent this, right, as an equation. So the equation for arithmetic sequence is t of n is equal to a, okay, plus n minus 1 times d. So a is always going to be the first term value, that first number in the sequence, okay? And the n represents the position in that sequence, okay? So if I'm trying to solve for, you know, the 21st term, 21 will be my n value, okay? And then we're going to do a minus 1, and d is the constant that we talk about, the difference or the distance from one value to the next. So looking at this example on page 3, we would see that we have 4, 7, 10, 13, 16, 19, okay? And here it gives you the A, but when you look at this sequence, you know that, okay, what's A? A is 4, that's the first value of the first element, right? And the distance, how can I find the distance? You would take one term and you subtract it with the previous term. So if I take 7 minus 4, I get a 3. If I take 10 minus 7, I get a 3. 13 minus 10, I get a 3. So my D is going to be 3. So using this formula, what we will do is we can find the next term, right? And in your head, you can say, oh, 19 plus 3, that's easy. That's 22. Well, let's see if the equation works. We have A is 4, and we're going to add that, okay, with n minus 1 times d, and our d is 3, and we already know that, okay? So the n, 1, 2, 3, 4, 5, 6, 7. So we're trying to solve for the 7th term. You're going to plug 7 in here. 7 minus 1 gives you 6, okay? So that will give us 3n plus 1, or 3 times 7 plus 1, which is 22. Okay, so for arithmetic sequence, your D is always the same. It's constant. Okay, let's look at the next example. Okay, so in this one, we start with -7, then we go to -1, then we go to 5, then we go to 11. We already see this distance is 6, right? Without even looking at this value. Okay, so how do I know that? I would take -7, subtract -1, okay? So the distance between this value and this value is 6. You count up 6, right? And then -1 with 5 is a 6. 5 with 11 is a 6. Okay. So if we need to find the 7th term, we simply use T of n equal to A. A is your -7. Okay. Plus 6. 6 is your D times n minus 1. Okay, so 7 minus 1, which gives us 29 as the output. Okay, so in this part of the notes, it shows you how you can apply that formula to be able to solve, right, for the term in the nth position. Let's look at our assignment. So for number 4, we're given 13, 16, 19, and we need to determine a value down that sequence. So it asks us for the 4th term, right? And then we want to write f of n equation or t of n equation to represent that. So we can use the first technique that we learned, or we can use the equation, which is easy. So we first say that your A is 13. The D, we can take 16 minus 13, we have a 3, or 19 minus 16, you also have a 3. So 3 is your D. And so when we solve for T of 4 or F of 4, we would have 13, which is A, plus N, which is 4, minus 1 times 3. And when you solve for that, you should get 22. And we can validate that by saying, okay, well, the distance is 3, so 19 plus 3 should give me 22, check, right? If I plug in, if n is equal to 4, right, I should be able to solve that because my f of n is 3n plus 10. Okay, so the second part to derive this function is when, remember the first approach that we had? We have to first come up with, right, how that would be represented to the nth value or the n position. So you will likely see questions, a few questions like this on your final exam and your next quiz. Okay. And it would ask you to determine the value for, let's say, the 20th term, or what is the function for the sequence, and then you have to pick the right option. Any question with 4? Okay, good. So it seems easier now that we see the formula, right? So the best part is that you already have the formula to work with, or the equation to work with. You just got to know what value is what, right? You know what A is, what D is, what N is, and then you plug everything in and you get your output. Or right? We can go through and we can just, but when you use this technique, when you plug in the n, what if you're trying to solve for n is 500, right? That's going to be very long. So the equation definitely help us reduce the work, okay? All right. So let's take a look at the next question. For number 5, it asks you, which of the following options is an arithmetic sequence? Okay. So when you see anything with the exponent like this, right, n to the third plus 2 times n, that's not, because we're going to talk about geometric and other type of sequence after this, okay? So when you look at a sequence like 8, T of n is 8 times n, we can say that, okay, so the first number is 8, the next number is 16, 24, 32, and so on. That is an arithmetic sequence, right? Because if you take 16, subtract 8, that's 8. 24, subtract 16, that's 8. 32, subtract 24, that's 8. So you would see that the difference, the distance between one value and another, right? It's incrementing by 8. It's adding 8 to each one, right? Subsequently. So that means that this is an arithmetic sequence. So A checks true. For D is -9 plus 6 times n minus 2, right? So if you solve for T of n, where n is 1, 2, and 3, you're going to see a pattern. Okay, so we go from -15, the next value is -9, right? The next value is -3, and after that there should be 6, negative, you add 6 with it in a difference. So it will be 3, I'm sorry. So the answer for this would be A and D, right? And if you're not sure about the other ones, you can plug in the n for like maybe 3, 1, 2, and 3 for n, and then you can see if there's a pattern. Okay, so for 5, we would choose A and D. But for quiz and test, there will only be one right answer. I don't do multiple right answers. Rarely I do. I sometimes do it in games, but sometimes it confuses students. So Jason said that all arithmetic sequences should be linear equation for the real numbers. Yes, that is correct. And then we'll talk about geometric next. So yes, it is linear. All right. So let's do another one with solving the arithmetic sequence. So in this one, instead of giving you the sequence, I want you to build the sequence. Okay. So we would start with T of 1. And we would have, because T of n is 5 times n minus 2. So we would have T of 1 is equal to 5 times 1 minus 2, which gives us 3. T of 2 is 5 times 2 minus 2 gives us 8. So we simply just plug in the n value into this, right? T of 3 is 5 times 3 minus 2 gives us 13. And then T of 4 is 5 times 4 minus 2 gives us 18. So that's good. So we have 3, 8, 13, 18, and we can put dot, dot, dot. So we have a partial sequence there. Okay. So the answer for that would be like this. Okay. So in this case, what you have to do is you give in, right, your f of n or t of n equation, and then you just take that, plug in the numbers to get your sequence values. And then you would have your partial of the sequence, meaning that we have the first few numbers. Similarly, you're going to see that for number 7. So we're given t of n is equal to -4 plus 8 times n minus 1, right? And this is pretty close to what we've seen in the equation earlier. Okay, so we see that this is going to be your a plus d times n minus 1. So we start with t of 1, we plug in the 1 for n. So when you do that, you have -4 plus 8 times 1 minus 1, which is 0, right? 8 times 0 is 0. So the first value is -4, which is here. Then you would do n is equal to 2, plug in 2, and solve for that. So 2 minus 1 gives you 1. 1 times 8 is 8, plus -4 gives us +4. Then t of 3, 3 minus 1 is 2. 2 times 8 is 16. Okay, 16 minus 4 is 12. And so on. So once you build out the first few, that's good enough. We can say that our sequence is -4, 4, 12, 20, ... Now, why is this important, right? So in sequence and series, you a lot of the times this plays into analysis and also providing, given certain set of data, you have to look for trends, okay? And then if you look further into how machine learning is really incorporated, basically you feed it data and it's looking for that trend. Implementing the algorithm for that trend is going to be the software developer, the engineers, right? Okay. Any question with 6 or 7? So we simply just use the same technique that we have for 6, and we would do that for 7. Okay. So now we're going to transition to geometric, and then we'll do series. So in geometric sequence, so in the last one, when we talk about arithmetic, we talk about distance, right? And we said that we would add each value by that same constant. In geometric sequence, we would then use a value and we would multiply it. So we would multiply it by the same constant. So it says in geometric sequence, each term is found by multiplying the previous term by a constant. A geometric progression or geometric sequence is a sequence of number where each term after the first is bound by multiplying the previous one by a fixed non-zero number called common ratio. So a geometric sequence is a sequence that each term equals to the preceding term times a constant, right? It's the same, it's just different verbiage to really explain the last few sentences. So you would then start with the first term, which is A, and then you would take that, you time it by the common ratio, which is R. And that would give you, I'm sorry, I forgot to change this to exponent. That would give you a times r for the second term. And then the third term, that will be a times r squared. And then the following term will be a times r to the third, and so on. Okay. So with that, what we have is we have a formula. We have an equation. Your t of n is going to be equal to a, which is the first term value, times r times n minus 1. Okay, so in this example, what you have is in 11.14 on page 4, you have 2, 6, 18, 54, 162 is a sequence. So if you only given this, we can say that a is 2 and r is 3. How do I know it's 3? If I take 6 divided by 2, I get a 3. 18 divided by 6, I get a 3. 54 divided by 18, I get a 3, and so on. So each of these, right, they would then take that value, multiply it by 3 to get to the next one, and so on. So if we're trying to solve for t of n, we simply can use this equation and plug in the n value, the a and the r value. So we can plug in the 2, we can plug in the 3, and then we can plug in the n. So if I'm trying to solve for t of n when n is 6, right, I simply plug 6 in here, and 6 minus 1, that gives me 5. So 2 times 3 to the 5th power. Okay, which is 486. Then for the next example, you have 1, -4, 16, -64, and 256. So a clue when you start seeing every other value is a positive, or every other, the second, the fourth, and so on is a negative like this, when it's switch sign like this, you know that we're going to multiply it by a negative, right? Your common ratio is a negative value. So based on the given sequence, we know that a, the first number, is going to be 1. So your a is 1. And your r, if you take the second value divided by the first value, you would get a -4. Or 16 divided by -4, you also have -4. So your r is -4. Then if we apply this equation for t of n, and if we're trying to solve for n is equal to 6, then you would take 1, which is a, okay, times r, which is -4, and raise it to the power of n minus 1, and 6 minus 1, which is 5. So 1 times -4 to the 5th power, which gives you -1024. So with that, we can look back into the assignment, and we would look at question 8. So it says select the options that represents the geometric sequence. Okay. So we can say that A, because A is T of n equals to 10 times 3 raised to the power of n minus 1. And that's pretty close to what we've seen with the equation, right? So if you look back into this equation, okay, we know that geometric sequence would be something like this. Then A would be close to that. Okay. What about B? Well, our first value is 1, okay? And then subsequently, you would see that it is multiple of 2, right? 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. So yes, that is also a geometric sequence. So would you always multiply? Yes. For geometric, you always multiply. For arithmetic, you always add. Okay, so that's the true difference between the two. Arithmetic, add. Geometric, multiply. You can multiply by a fraction, which is divide, right? You can add by a negative, which is subtraction, but okay, so, okay. Now, what about C? Looks kind of like this, is it? Right? If you're not sure, test it, right? Test it with plugging in 1, 2, 3, 4, and you can see. Okay. A big clue is this right here. Okay. You adding with a constant. So no. So that's more arithmetic than geometric. What about this option? Again, adding. No. So only A and B. Okay. Okay. So let's solve for, let me move this up. I don't know why it's so far down. Let's solve for number 9. So you have T of n is 64 times 1/2 to the power of n minus 1, right? We want to create a geometric sequence given the equation. So then we would first plug in T of 1. We plug in the first n, which is 1, and we would have 64 times 1/2 raised to the 1 minus 1 exponent, which is 0. So 1/2 to the 0 is 1. 1 times 64 is 64. T of 2, 64 times 1/2 raised to 2 minus 1, which is here in the exponent, that will be 1. 1/2 to the first is 1/2, and 1/2 times 64, that will be 32. T of 3, we would have 64 times 1/2 raised to 3 minus 1. And so 3 minus 1 exponent, that will be 2. 1/2 to the second, that will be 1/4 times 64, that gives you 16. And so we can continue, but the partial sequence we have 64, 32, 16. And the next one should be, anyone know? 8, right? It's dividing by 2 subsequently. So the key here is we look, okay, how it's going to be multiplying. So your R is the common ratio, which is half. Any question with 9? Okay, so definitely you're gonna get geometric and arithmetic progression on quiz and exam. So make sure you know how to solve for those. For number 10, we have T of n is equal to 37 times 2 to the n power. We want to create a geometric sequence. So again, we will plug in 1, 2, 3 for n. So in the first one, you have t of 1. That will be 3/7 times 2 to the first. That will give you 6/7. T of 2, 3/7 times 2 to the second, which gives you 12/7. T of 3, 3/7 times 2 to the third, which gives you 24/7. So we generated the values. We can then put it in a sequence, 6/7, 12/7, and 24/7. So we can see that your ratio is 2. Okay, any question with 10? So similar to number 9, right? We just simply use the given equation. We plug in each n value from 1. And then we go 1, 2, 3 for the n value, plug that in, solve for t of n. Then we have partial sequence. And this one is geometric because we can see that there's a common ratio, which is a value that's being multiplied by each term. Okay. Any question with these before we move over to quadratic? So for quadratic sequence, we would look at the sequence in that the nth term is given by the quadratic functions. And if you worked with quadratic functions before, right, graphing it, solving it, looking, some teachers would teach you FOIL technique, right? On this one, so the equation for quadratic sequence is a of n is equal to a times n squared plus b times n plus c. So when we're looking at the examples 11.16, we have 1, 4, 9, 16, 25, 36. So we can see a pattern, right? So if n is 1, you have 1 squared. When n is 2, you have 2 squared. When n is 3, you have 3 squared. When n is 4, you have 4 squared, and so on. So your a of n here is n squared. And then for your next example, you have 6, 15, 28, 45, 66, and 91. Okay, so going from 6 to 15. Okay, so how can you represent that? So for the first one, when n is 1, if you square the n, multiply by 2 plus 3n plus 1, then you would have 6. Okay. So in quadratic sequence, you would have quadratic representation in the equation right here. See that? See that there? So you're going to look for that in how that will be for t of n or a of n. Okay, so here it kind of bring back what we talked about when we talked about arithmetic. So earlier Jason said arithmetic sequence is always a linear function. Yes, right. So arithmetic sequence is represented as a linear function. because we would add a constant to get the successive term. In quadratic sequence, the difference between successive term is given by a linear function, and there's the second differences are constant. So there are two levels of differences. So the first level of difference in quadratic is a linear function, and the second level of difference is a constant. Okay, what do I mean by that? Let's look at 1118. So let's say that we have this sequence 6, 15, 28, 45, 66, and 91. First, we need to take a look at the first level of difference for each of these numbers. So if I take 15 minus 6, right, I get a 9. 28 minus 15, I get a 13. 45 minus 28, I get a 17. 91 minus 66, I get a 21, and so on. There's a pattern in the first level of difference, which is a linear, right here. So we can see that it is incrementing. Okay, so when you approach this, first you're going to take the sequence, you would subtract, right, the two consecutive terms to get the first level of difference. Then you would take the first level of difference, then you subtract the consecutive terms to get the second level of difference. So if I take 13 subtract 9, I get a 4. 17 subtract 13, I get a 4. 25 subtract 21, I get a 4. So in the second difference, it's a constant. First level of difference is a linear function. Okay. So what we want to achieve out of this is to evaluate the first level of difference and the second level of difference. So that way we can solve for A, B, and C, which would then give us, right, the actual equation for that sequence. Okay. So let's take a look at example here. So earlier we saw that how we subtract, okay? Now, when you plug in n is equal to 1 for the first step, you would then, just like when we started the session today, you plug in the position value, which is n, okay, into this. So when I plug in n is equal to 1, I have a times 1 squared plus b times 1 plus c, which gives me a, b, c equal to 6. Then I would put in n is equal to 2 into this equation. I would then have a times 2 squared, okay, 2 squared, plus b times 2 plus c is equal to 4a plus 2b plus c equal 15. Then I'm going to go again, n is equal to 3. A times 3 squared plus b times 3 plus c gives me 9a plus 3b plus c is equal to 28. Step number 2, once we have the ABC equations, after we plug in the n values, then we're going to take the two equations, the two ABC equations, and we're going to subtract them. Okay, so subtract the first equation from the second equation, and then the second from the third to get the difference, right? We're trying to achieve the difference. So I'm going to take the highlighted ones, which is 4a plus 2b plus c equal 15, subtract a plus b plus c, and I simply just line up the variable as I subtract them. So 15 minus 6 gives me 9. C minus C gives me 0. 2B minus 1B gives me 1B. 4A minus A gives me 3A. So the difference outcome, the first level difference, is 3A plus B equal to 9. Okay. Now, then I would take these two and find the difference. Okay. So I would take 9A plus 3B plus C equal 28, subtract the second equation, 4A plus 2B plus C equal 15. So 28 minus 15 gives me 13. C minus C gives me 0. 3B minus 2B gives me 1B. 9A minus 4A gives me 5A. So again, the first level of difference between the second and the third equation is 5A plus B equal 13. Okay. Then after that, we have to find the second level difference. Okay, by taking this, subtract each other, then we would then narrow down to a variable, solve for that variable, then plug it in, solve for the second variable, then plug it in, solve for the third variable. So our objective when we find the level of differences is what? Coming back to earlier in the page, it says for you to solve for ABC. If once we solve for ABC, then we can put together an equation that would represent A of n or f of n. Okay, so now after we find the first level of difference, then we would take these, okay, and then we would operate the subtraction to get the second level difference. So if I take 5A plus B equal 13, that's from the step 3, minus 3A plus B equal to 9 from step 2, I have 2A is equal to 4. And then from there, I can solve for A, right? Divide both sides by 2, which gives me A is equal to 2. So now I already have one variable, which is A. Okay. Then I would plug it back into the ABC equation to solve for B. So if I already have A, I plug A in. So 2 times 3 gives me 6. 6 plus B equal to 9, so B must be 3. Okay. So once you have the A, then you're going to work upward or backward to each of the difference to solve for each variable, right? So now I have A and B. My A is 2 and B is 3. Then I just have to solve for C. So now I went from the second level of difference to solve for A to the first level of difference to solve for B, right? And then coming back here to the first step to solve for C. So then I would plug in A, which is 2, B, which is 3, and C is not solved yet. So we have 2 plus 3 plus C is equal to 6. Where did I get this from? Well, if you look at coming backward to this step right here, right? We have ABC's, A plus B plus C is equal to 6. So we're at the first, at step 1 now, right? We're working back to step 1 now. So 2 plus 3 plus C is equal to 6. So C must be 1 because 2 plus 3 is 5. we subtract 5 from here and subtract 5 from this side. So C is equal to 1. Then once we have A, B, and C, then we plug it into the original equation, which is this guy right here. Okay. And then we plug A, B, and C in, and we should have 2n squared plus 3n plus 1 is your A of n. Okay. There are other approaches to solving this, but since we talk about the difference, right? The first level is a function, the second level is a constant. I want to show you that. Okay, so let's do this one and then we'll talk about series or partial sums. So for number 11, it asks you select the options that represent quadratic sequence. So quadratic sequence should look like quadratic formula, right? And we mentioned that it should have something that would represent a times n plus b, or n squared plus b times n plus c. So this looked like that. So option A. And if you're not sure, you can plug it in, right? Or look at the level of differences. You can plug in n, solve for n, and then look at the pattern there. D is also another quadratic sequence. Quadratic is the easiest, right? So all of them are easy, but when you look at quadratic sequence, it just jump right out. The square, right? And the quadratic format. So A and D for number 11. So for question 12, it asks you, what are the differences between arithmetic sequence and quadratic sequence? Earlier, we said the arithmetic sequence is a linear function, and the difference between successive terms is a constant. In quadratic sequence, the difference between successive terms are given by a linear function, and the second differences are constant. So there are two levels of differences in quadratic sequence, right? Whereas arithmetic sequence only have one level of difference, in that all the successive term is, the difference in successive term is a constant. And you can find all of the verbiage in the notes as well, right? I highlighted or bolded the section, so you can always go back and copy and paste it over or type it. So make sure we know the differences, right? At the end of the day, right? For our quiz, our tests, and also all your exercises. So any questions so far? So for number 13, it's very much like the example we just touched on. So for 13, we are given the quadratic sequence, okay? 4, 8, 11, 13, and 14. Then what you would do is you would then if you wanted to look at the level of difference, right, when you subtract 8 with 4, you get a 4, 11 with 8, you get a 3. So you see a decrement in the difference level 1, and then you take those, you would then find a second level difference by subtracting. You have a distance of 1 in all the successive difference values. So if we're given this equation, a of n is equal to n times a squared plus b times n plus c, then we would start with for n is equal to 1, we would have 4 equal to, right? 4 is the first one. 4 equal to a times n squared plus b times n plus c, which is ABC equal to 4. Then for the next step, for n is equal to 2, and the second term is 8, so we would have 8 is equal to a times 2 squared plus b times 2 plus c. Okay, when you multiply everything out, you should have 8 is equal to 4a plus 2b plus c. For n is equal to 3, we would have 11, which is the third term, equal to a times 3 squared plus b times 3 plus c. Multiply everything out, we should have 11 equal to 9a plus 3b plus c. Okay. Any questions so far with these steps? So we simply put in 1, 2, or 3 for n. Thank you for that. And then to be able to get the equation to ABC, right? Now we're going to do the subtraction. Sorry, I'm a color highlighter person naturally. So I just wanted you to see how each of these are going to be different steps. So the difference in level 1, then you're going to take these. Okay, so I took this one and this one, and I operate the subtraction. Okay, so 4a plus 2b plus c, that comes from here, equal to 8. Subtract a plus b plus c equal to 4 from the first one, from n is equal to 1. So I take the n is equal to 2 output, subtract n equal to 1 output. So when I subtract, I just line them up. Okay. Yeah, no problem. I line them up. So if 8 minus 4 gives me 4, c minus c gives me 0, 2b minus b gives me b, 4a minus a gives me 3a. Okay. Then again, I would take the second and the third one. So when n is equal to 2, the output of that, and n is equal to 3, the output of that, and I line them up and I would do the subtraction again. So here is this one at the top, subtract the second one. Okay, so 9a plus 3b plus c equal to 11, minus 4a plus 2b plus c equal to 8. What I have is then I would 11 minus 8 is 3, c minus c is 0, 3b minus 2b is 1b, 9a minus 4a equal to 5a. So once I have the difference level 1 solved, I would take the yellow highlights and subtract them. Okay, so I take the 5a plus b, put it at the top, subtract 3a plus b, put it at the bottom. And so I have 3 minus 4 is -1, b minus b is 0, 5a minus 3a is 2a. So now I can solve for a, and that's the objective, right? We said that when we subtract to get these level of differences from level 1 to level 2, our goal is to solve for a, b, and c. So at this point, what you have is you have a is equal to -1/2, because I would take -1 divided by 2 to solve for a, and that will be -1/2. Then once I have a, I plug it back into the level 1 difference to solve for b. So I chose that one. And so I would have -1/2, which is a, times 3 plus b is equal to 4. So then I solve for b, and b should give me 11/2. After I plug everything in, multiply it, and then subtract it or add it, right? Because negative with the negative is positive. So I have 11/2 for b. Now I have a and b, then I would plug it back into the ABC equation to solve for c. So I have a is -1/2 plus b is 11/2 plus c equal to 4, right? This one is a long one, so it goes into the second page. So after that, I should have 5, right? 11/2 minus 1/2, that's 10/2, which is 5. 5 plus c equal to 4, so c is -1. So once I have a, b, and c, I would then plug it back into the original equation, right? A times n squared plus b times n plus c, then I would have a of n. So c is -1, like I mentioned. Then we plug a, b, c in and into the quadratic progression equation. Then I would have a of n is -1/2 times n squared plus 11 over 2 times n minus 1. And at that point, you can solve for any value of n. So if I'm looking for, n is equal to 73, I just plug that in and be able to find the value for the 73rd position in that sequence. Any questions with this one? Okay, good. All right. I hope I don't go so fast, but we still have a little bit left to cover, which is sum and series. Okay. We're gonna talk about Gauss trick, which is fairly short anyway. Okay, so refer to your notes. It walks you through the steps, right? Okay, so the next part, we're going to talk about series and partial sums. So series is the sum of the terms of the sequence. And since the sequence had indefinitely many terms, the series is the sum of infinitely many terms. So when you say series, it is actually the sum of the sequence. Okay, because people mix them up. And after this class, I hope that you're clear. Sequence, right? We talked about sequence. There's different type of sequence. They are progression, okay? It represents a pattern, and we would look at how successive term is derived based on the prior term. And could be the distance or the common ratio, the relationship between one term to the next term. Series is the sum of the terms in the sequence, okay? So when we're looking at arithmetic series, that means that it's the sum of the arithmetic sequence. Geometric series are the sum of the geometric sequence. So here what it shows is that when we add up all the terms, right, in that sequence, we would have the series. So now there has to be a better way to solve this, right? And here comes Gauss trick, arithmetic sum. So when we do the arithmetic sum, right, let's say that you have to add up 100 values in that arithmetic sequence. That's going to be a long time. So we want to be able to find a better way to solve for it. So we have what's called Gauss trick. And Carl Friedrich Gauss, he came up with this at the young age of 8 or 10 or something like that. His teacher, right, decided that he should, you know, just keep him busy. He should add up the values from 1 to 100. And when he had to do that, he wanted to spend the least amount of time to do it as possible. So he came up with a solution. Okay. So if you're looking at the integers between 1 to 100, you would take the first value, which is 1, and the last value, which is 100. And you add them up, okay, first and the last term. Then you would take the number of terms in that sequence and you divide it by 2 and multiply it by that sum. Okay? So that way you would get the arithmetic sum or the arithmetic series for that sequence. Okay, pretty clever. So in that case, right, in his situation, he would take 1 plus 100, that's 101, and then be able to take the 101, multiply it by the number of terms divided by 2, which gives you the arithmetic series. So when we look at this example, right, when you do 100 plus the 100 plus 1, which gives you 101 times 100 divided by 2, because there are 100 numbers in that sequence, okay, that gives you 50/50, okay? And in the second example, example 1120, you have 1 plus 2 plus 3 plus etc. plus n. Again, you would take n, plus 1, right? Because this is the last number plus the first number, okay, right here. Multiply it by the total number of terms divided by 2, which is n divided by 2. So, okay, or we can sit there and add it up forever. So let's try. So for the test, just know how to do Gauss trick for arithmetic series. Determine the arithmetic sum for the following sequence. Okay, and we are going to do a partial sum. We're only going to do the ones that are given here from -72 to -12. And sure, you can punch this into your calculator and then be able to provide the result, or we can apply the formula. So your first value is -72. The last value is -12. Okay, so you would take those and add them together first. So you would then have, I don't know why I put double parentheses there. Then you would have what, 72, -72 subtract 12. That's going to be -84. Then you're going to multiply it by the number of terms divided by 2. So if we're looking at 1, 2, 3, 4, 5, 6, 6 divided by 2, which is 3, right? 3 multiply it by, I know why now that I put the double parentheses, by -84, which gives you -252. So the partial sum for this arithmetic series for the first 6 values is -252. Okay. Any question with number 14? We only have 15 left, so not bad. Okay, and you can always go back to the note, check out the example, right? Work with the example and see if you get the same result using Gauss trick. Then geometric sum series. Geometric sums are geometric series. So now, remember earlier we talked about common ratio, right? And in the geometric sum, we would have the R, which is the common ratio, the R. Okay. So here it shows you can sit there and you can add them all up, right, and get the sum, or you can apply the formula. Okay. So the important part about utilizing this formula is to identify your common ratio. Okay. So all of these examples shows, right? There's one with the R is equal to 3, right? And then you can add them up. So now when we look at the equation, this is your magic equation, okay, on page 8. So when you look at the geometric series, A is the first term value, just like the other equations that we worked with previously, right? And R is your common ratio and N is the number of terms. So your equation is A times N minus R to the N divided by 1 minus R. Okay, so 1 minus R to the N divided by 1 minus R. Make sure that we apply the parentheses accordingly. So you operate inside first, then you multiply it out. So using this, we can solve for the next problem, which is number 15. So in 15, it tells you find the geometric sum for the first 4 terms in the sequence. And yes, you can find the partial sum, right? You can find, you know, the sum for a larger partial, right? So yeah, we can punch this in the calculator. We can manually add it in our head, but we wanted to apply the formula so you can see. So we have 10, 30, 90, and 270. So quickly you can say that the common ratio is 3, because if we take 30 divided by 10, we get a 3. If we take 90 divided by 30, we get a 3, and so on. Now, then next we would identify the A, which is 10. So when you use these formula or the equations, it's important that you first, right, identify what that first value is, which is the first number in that sequence. And then in the geometric series, then you would have the common ratio, which is 3 in this case. And we were asked to find the sum of the first 4 terms, so your n is 4. Okay, I should type in n is 4. Right, some equation shows k, but it's confusing, so we keep it the same like what you've seen in your notes. N is 4. So applying this, what we would say is we would take the first number, which is 10, times, okay, 1 minus 3, which is your r, to the 4th, that's n, right? Divided by 1 minus 3. So after you raise it to the exponent, take the subtraction, do the subtraction here, do the division, then you get the result from the inside, then you multiply it by 10, so you should get a 40 times 10, which gives you 400. Okay, so 400 is the total for the first 4 values in that sequence. You can add it up in your head quickly. It should give you 400. 10 plus 90, that's 100. 30 plus 270, that's 300. So 100 plus 300 is 400. And you can test it with the larger value, right? What if I wanted to add up the first 5 or the first 8? Then you can apply that equation or that formula. Okay. So it's good to know how to apply the formula if you remember the formula. Okay. And for our tests, for our final exam, it's closed note, closed books, and I use Lockdown Browser. So we have plenty of practice with our assignments and things like that. So go back, look at your notes, practice. If you're not sure, right, you want to get a little bit more, understanding on it, then you can do that. Okay, any questions in the last 2 problems that we solved? With no questions, I will end my session. Please add your name to the chat. Thank you for attending tonight. And I will see you on Wednesday for lab. Have a good night. And if you didn't submit the last lab, work on it and submit it so I can update your grades. Thank you. Have a good night. Yeah, no problem, Juan. I understand. If you miss anything, you have questions, let me know. I'll stick around for a few minutes. Hey, Eric, how are you? Okay, yeah, no problem. Have a good night. Okay, I'm glad you attended. Thank you. You too.